two nitrogen here. They both look pretty similar. This nitrogen 1, 2, 3 bonded it with a lone pair. That nitrogen 1, 2, 3 bonded with a lone pairs. Really look similar. That I would say is sp3 hybridized. Just like the same reason. 1, 2, 3 bond, but lone pairs has to go somewhere. So we can consider lone pairs another bond. Hence, it has to make up 4 substitutions, and then sp3 will have 4 sp3 bonds there. Does it mean that this is sp3 hybridized nitrogen? It looks similar. But if you kind of write it down, that nitrogen sp3 hybridized, you are wrong for the same reason. One of the things that you really have to be careful in organic chemistry, something looks similar, may be different. So don't try to make an argument later. I solved a similar question. Answer was this. Why that question tells us different answer? Because they are identical. They're different questions. It may look similar. That's why you maybe fall in to the parallel solving that you did while you studying. But you've got to look at the things very whole, not just analyze. So I'm trying to warn you. You've got to be careful about a similar looking question, but end up having a different answer. So this is one of the situations we can see that they really look identical, except these carbons are all made of a single bond. There's double bond there, but the thing is, having double bond here, that's the one thing's different. It makes the resonance structures. You cannot make a resonance structure with this one, but that one, yes, you can. This lone pair comes in, make the carbon nitrogen double bond, and then one of these double bond goes out, that makes an anion right here. And this can move around the ring, goes in, comes out there, negative charge here, goes in, come out there, negative charge there. So it makes a minor contributors because there are many structures of broken. And they also charge separation, and also make the carbon negatively charged. But I mean, still, these resonance structures exist. What that means is nitrogen here should be able to make a double bond with that carbon. So you cannot do that with an sp3 hybridized nitrogen. You can only do that with an sp2 hybridized nitrogen. When you look at this resonance form, sp2 is obvious. It's easy. Double bonded nitrogen got to be an sp2. But you got to remember this can be created from that form. We're only going to show this form in the test. So figuring out, can you make a resonance structure or not, is still a very important question for this question. So that's the reason resonance structure is something you really have to know. Whether you can make it, what it's going to look like, how many is going to make it, what are the major contributors, what is minor contributors. Anyway, so it's kind of the same question. When the nitrogen can make resonance structures, these lone pairs can go p orbital by having it sp2. All right, so that's basically what I want to talk about using these examples. Continuing on, I know I'm kind of being overly excessive here, but really, we always ask this question. I don't know why we always have someone who doesn't answer properly. So. Okay, this question is a little bit more complicated. We got not a double bond, now I have a triple bond there. So let's look at that. That carbon there is an obvious. If I look at what's the hybridization of that carbon, you should say sp3, right? Even though it has a 2 principal bond, one carbon, another carbon bonded there, but it's supposed to have 2 hydrogen, which is we don't normally show the line of drawing. So this carbon gets sp3 hybridized. That's simple. Double bonding carbon, right? Even though we don't, that's the something you got to imagine. This hydrogen here. So this carbon is a 1, 2, 3 substituents and double bonded it. So this carbon is an easy sp3 hybridized. What about that nitrogen? That nitrogen makes a double bond to the carbon too. So that lone pairs are here, not the hydrogen, right? And then this nitrogen sp2 hybridized, just like this one. This carbon here, right there. There's a carbon. Every junctions, right? Suppose they have a carbon, that's a line in the drawing. Triple bonding, we draw this way because it's linear shape. We don't angle the triple bond because of course it's 180 degrees. So this carbon, hybridization of this carbon to triple bond, one bond, it makes another bond with the nitrogen, two pi bonds. So this has to be sp hybridized. I want to discuss it very first place. And that nitrogen down there, it makes a triple bond with the carbon. I notice only one bond here, but it also has a lone pair. Right? Nitrogen have a lone pair. So if these are possible two slots, one and then the other one for this carbon, so sp will hybridize nitrogen again. So triple bonded one, sp, double bonded one, sp2, single bonded one, sp3. That kind of works well for the carbon. For nitrogen, you gotta be careful, but if they don't make a resonance structures, if you include the lone pairs of substituents, it still works pretty similar as a carbon. Now I'm going to talk about where this lone pair is. Nitrogen lone pairs can be in different places depending on the what hybridization is. This nitrogen makes sp2 hybridizations. One is making this bond, another make that bond. Third one is available, but no substituent. So that's the way the lone pair goes. The lone pair of this nitrogen goes sp2 hybridized orbital, not the p orbital, right? And then this lone pair on that triple bonded nitrogens, that goes to which orbital? P orbital. This nitrogen is sp hybridized. They're supposed to be created, it's supposed to create two sp orbitals. One is used to make a bond with that carbon. And then opposite side, there's another sp orbital there. Right? That's the where this lone pair goes. It goes to sp hybridized orbital. Not the p orbital, right? I mean, sometimes I keep stressing on those lone pairs of nitrogen that makes a resonance structure for the p orbital. Everybody just keeps saying p. I know it's trying because they didn't know the answer, so they just want to take a chance. But you got to be able to figure this thing out. It's not that hard. Look at that one. There's a two nitrogen and one oxygen. Carbons are simple as I said. It's double bonded carbon, sp3 hybridized. No, that's easy. But this nitrogen with this nitrogen having only 1, 2, 3 bonded there, but we all know it is a lone pair. The possible 4 places available. So that's sp3 hybridized nitrogens. And then the same reason that lone pairs is going to the sp3 hybridized of the nitrogen. But this nitrogen, that's the thing we just talked about. That makes a 1, 2, 3 bond, just like this one. And that nitrogen also have a lone pair too, but it's not sp3 hybridized. Why is not sp3 hybridized? Because it makes a resonance structure with a carbonyl in its place. This is the exact same thing as the one we just discussed in the previous slide. If these lone pairs comes in, they got double bonds. And then this pi bond goes to oxygen as an oxygen anion. So that's a minor contributor it makes it. So that means if this nitrogen, this has to be sp2 hybridized orbital. Then, if it is sp2, where this lone pair is supposed to go? It cannot go to sp2 because all sp2s are used to make a 3 bonded there. So only thing left, the p orbital. So this is the one that goes to p orbital. That one, yes. That one has a 3 loop. Yes. So that's a good question. So then this oxygen, I didn't have it there. That is supposed to be sp2 hybridized because it makes a double bond there, right? If you look at that one, that's going to have a 1 single bond with a 3 lone pairs, so it could be sp3. So what will be the hybridization of this oxygen? It's going to be sp3 like this, or it's going to be sp2. It cannot be sp3 because if it's sp3, then we cannot explain that. But this can be sp2. How are we going to explain those 3 lone pairs as being sp2? This oxygen has 3 sp2 orbitals. 1 used to make this bond with the carbon, 2 for the 2 lone pairs. And then there's another lone pair left over. Where is going to go? Or the leftover, p orbital. So it has 3 lone pairs, two lone pairs go to two sp2 orbitals, one go to the p. So we can explain that. So that's the kind of a complexity you have to deal with. Yes.
Charge separated carbons drawing the station. Like let's say there's a lone pair, and you give that lone pair, give carbon a lone pair, it would be a minor structure, but still it's impossible what to.
Yeah, if that participate in making resonance structure, that lone pairs cannot be one places. So even if you draw one form, you still have to consider resonance. And then whatever the hybridizations, it has to be explained both. It's for the same reason. So when the carbon get negatively charged, it's going to have a lone pair. It's going to be a similar situation to nitrogen. Having a lone pair.
But you can break a double bond and put a lone pair on carbon. So there's a problem there.
Yeah, that depends on the example. I mean, even though this lone pair is nitrogen, but this one doesn't make a resonance structure. So if it doesn't make a resonance structure, then they're not going to do. So sometimes that's the reason. Sometimes you got to find out whatever the resonance you draw is a valid or invalid. I probably want to ask that question first. Because if you kind of make an invalid resonance structure, try to work it out, then you're bound to have a wrong answer. All right, so this is kind of the things that you need to go over that. We just talked about that simple reason. Oxygen have two lone pairs. They're supposed to be sp2 or hybridized oxygen, two lone pairs go to sp2 orbitals. And that's basically what we just talked about. All right. This question is I'm bringing here a little bit too early. I know that, but we still can talk about it with the resonance structures and these hybridizations. But we're going to talk about this particular thing in detail, much more in detail than we can do. We got nitrogen here. We also have nitrogen there too. This nitrogen is something we already talked about in the previous example. So this is something that I thought you can handle. Yeah, that nitrogens are doubly bonded with this carbon, and then lone pair there. So, what hybridization do you think this one has? sp2, right? Where is lone pair supposed to go? That goes to p orbital or sp2 orbital? It makes an electron pairs in the p orbital. That's what makes a double bond here. So it doesn't need to go to the p orbital. This one goes to sp2 orbital. Sorry. So that's basically what you saw in the previous slide. At least that is not too hard to get. Look at this one. There are two nitrogens. This one looks very similar to that one. Doubly bonded it, right? And then there's a lone pair there too. So this nitrogen, if I'm asking you, what would be this hybridization state? You're supposed to say sp2. And then it is right. By the same reason, where this lone pair is supposed to go, is it going to be in sp2 orbital? And then, yes, it is also in sp2 orbital too, by the same reason. But what about that nitrogen there? This is the one that has a 1, 2, 3 bond there, and with a lone pair. But now you probably know that this cannot be sp3 because it makes a resonance structures, all of these double bonds in the ring system. So that is an sp2 hybridized nitrogen, as we just talked about. But this lone pair on that nitrogen is now an sp2. This nitrogen has a 3 sp2 orbital, but made a 3 bond with all these 2 carbon and 1 hydrogen substitute. So all of sp2 orbitals are used up. So where this lone pair is supposed to go, it goes to p orbital. And then because it goes to p orbital, it can make a resonance structures with all these other numbers. So this question, I can keep changing. I can keep adding on the ring. So there's no way you can memorize these things. You really have to work it out. And I'm going to make something really similar so you can fall into trap. So you really want to make sure that you understand these things. And these things are not really hard. I mean, once you study it, you get the hang of it. But right now, you just figure it out first time, so it makes it very confusing. And it's a simple counting. How many bonds does it make? What's what's the level orbital, what's the glow, what's the make resonance structures, you can probably make some formula for to solve these questions, but you gotta do it manually. All right, we've been talking about nitrogen. I want to talk about oxygen. I mean, it's kind of the same thing, except that oxygen has two lone pairs, not just one. For that one, there's an oxygen here. It makes a two bond, but it's supposed to have a two lone pairs. My question is, are these two lone pairs are on the same orbital? Or similar, same, or they're equivalently placed? My answer to that is not. So let me show you this. What's the hybridization of this oxygen? It looks like it's make a single bond here, right? So sp3, two carbon, two lone pairs. So that's something you would say, but now you know more. It can make resonance structures. It can keep making resonance structures. Basically, it's just circling around the way. So it's doubly bonded oxygen with a carbon. Of course, that makes the oxygen positively charged, but that's the one thing that we need to make sure that this oxygen has an sp2 hybridization. So this is sp2 hybridized oxygen. What it means is it only has a 3 sp2 orbitals. One make a bond with this carbon, second one makes a bond with this carbon, third one, this lone pair goes in. But there's another lone pair there. So where this lone pair goes, this one goes sp2, that one goes to p orbital. So oxygen has two lone pairs, but they are differently situated. This one's an sp2, that one's a p orbital. This one, what's the hybridization of these oxygens? Again, the oxygens supposed to have two lone pairs. It's an sp2 again, because most of the question I ask you is an sp2. Right? If you guess that way, then you're wrong. This one is an sp3. It doesn't make any resonance structure. And two lone pairs are exactly same order, sp3.